Good afternoon, this is Schweitzer. We're going to talk a bit about another ionic, I should say atomic trend. And this trend is the trend of ionization energy. Okay, so what is ionization energy and why is it important? Well, first of all, ionization energy is the amount of energy needed to remove an electron. So a couple things you might note about this is that, first of all, in order to remove an electron from an atom, I need to physically break an attraction. Okay, we need to break this attraction. This attraction is typically called Coulombic attraction. You must add energy to do that. You must add energy. You're not going to get energy back from this process. So I will lose energy. I'll have to invest energy in the system. Um, so you should realize that if I were to maybe add an electron to this thing, then that's the reverse process. So in this case, energy enters the system, energy enters. So theoretically, if I reverse this process, then energy should get released. And that is something that people are sometimes unsure of, but either way, just a side note, okay? So in this case, I'll be separating an electron from this thing. Now, why is it important? Really, for the most part, okay, so why is it important? Unless we are talking about a nuclear reaction, okay, adding electrons or removing electrons is a big part of our chemical reactions. This is just chemical reactions. So the easier you can do this process, the more reactive. So there's definitely a role of reactivity here. If you find an atom that doesn't want to gain or lose electrons, or it's very difficult to gain or lose electrons, energy-wise, then it will be very non-reactive. So there's a huge role of ionization energy in the role of reactivity in chemical reactions. So it's also a means by which we will, discuss how protons and electrons interact. That's probably within the atom. Within the atom. That's probably the reason why people in advanced placement and colleges use it the most. Is just to try and just test whether you understand how Coulomb's law works, how protons and electrons work around atoms. All right, so let's keep moving here. Which one requires more electron to remove? So let's revisit Coulomb's law. This is the inside the nucleus. Okay, this is the electron. So that's this guy right here is this guy right there, and this one is that guy. So it's shining out in all directions. Okay, and our attraction is just an electron and the nucleus. So just by this fact, and then of course this distance is this guy right here. Notice the square here, which means that that's more of an amplified factor. So in reality, how far you are away from the atom, the nucleus, really matters because of this guy. So which one's the hardest to remove? Well, okay, so which one is more to remove? So number one, let's go number one for the one that's hardest. Okay, right. Number one for the hardest. That's going to be this guy. Why? It's got the most charge and, well, now this is just the charge of an electron. That's the same for all of them, technically. That's the charge of this electron, and that's it. So, so this is the same. So this guy's got more positive charge here because bigger atom, but the distance is really small. So then when this gets small, this gets really big. Okay. So this is number one. Now we got these two. We got this one versus this one. Again, we want to look at this always in terms of Coulomb's law. You might say that this one should be number 2, or should this one be number 2? You might say, well, this one is number 2 because this guy's got more protons. Therefore, this is bigger, and therefore, this guy should be number 2. Or you could say this guy right here is bigger because it's got a smaller distance. Therefore, this guy should be number 2. Well, it kind of goes back to the situation of this squared law here. And we find in nature, and we're just creating a model that mimics nature. This is not, this is just, yeah. So the math doesn't do anything. It mimics what's actually happening. So apparently, distance is having a much greater effect. So the first thing we really look at is the most important factor here is distance. Therefore, this is number 2, and this one will be number 3. Okay. Which one is easiest to remove an electron from? That's the easiest electron to remove. Why? Because it's the farthest away, which is, again, reiterating that that distance is really a big factor. And to remove this interior electron, well, you might think you got to, as energy is applied to the outside of the atom, could be in the form of light, could be in the form of other electrons. Likely it's going to knock off all these other ones first before it gets to that one anyways. But if you could, with a high energy pulse, shoot in, knock the electron out, that one would require the most energy possible. And that is a feasible situation. All right. So let's review these concepts here. Why does it get harder to remove an electron as they move up the table? Well, that's simply because they get smaller. Okay? And not just a little bit smaller, a lot smaller. We're losing energy levels. Remember, each row of that periodic table represents an energy level. So every time we move up and down an energy level, we go from having one energy level to having 2 energy levels to having 3 energy levels. That electron is just super far away. It gets easier and easier to remove. All right, why is it harder to move down the row? Well, this is actually an example of effective nuclear charge. Now, you don't particularly have to know that term. You just need to know the Coulomb's law. Effective nuclear charge is just an example of Coulomb's law. Nuclear charge. Now, I also would tell people in upper level chemistry that if you don't understand or don't really know the word what that means, then don't use it. Only use it if you understand what it means, because it encapsulates this whole idea. So inside a row, keep in mind, now I'm not saying that the radius is the same all along, but it's darn close. We have the same number of energy levels. Okay, so let's just say we have 2. So my distance from the nucleus to an electron really isn't changing a ton across. Now this is the second one, so it would be this guy right here. It really isn't changing a ton. The distance is relatively static. Okay, it's not a ton. So now all we're doing as we move up and down this row is changing the protons. Remember, this is the charge on that electron, and this is the charge on the nucleus. So all we're doing is adding positive charge. Be sure we can add electrons. That's like taking, sometimes this nucleus in Coulomb's law is sometimes taking like a light bulb. And, all right, and it shines out light in all directions. Right? And you're standing out here looking at it. Well, if you had another person out here looking at it over here, does the light bulb get brighter? No. It's shining in all directions to everybody. Add more lights inside here, double that up to another light bulb or a higher wattage light bulb, we get more intensity shining in all directions. That's what this does. All this guy does is looks in and sees 3 protons. This guy looks in and sees 3 protons. All right. Add another proton, add another electron, maybe, you don't have to. Now this guy sees 4 electrons. And this is all based off Coulomb's law. Whenever we describe these things, Coulomb's law is a big factor. So why does it increase as we go down to the right? Well, it's got increased effective nuclear charge, or you could say this definition would be we have more Coulomb attraction okay, attraction due to more protons. And more protons at about the same distance. Okay. All right. Next one. All right. Again, which of these would be examples of nuclear effective nuclear charge? Well, that would be the one where you're moving within the row of a periodic table. So it's the one where we're going back and forth inside a row. Up and down is not effective nuclear charge. The nucleus is not very effective because you're adding energy levels, adding distance. Okay, so our general problem solving strategies are going to be identical to the last one. Now again, this is just kind of a procedure to follow, but really it's a procedure that looks at Coulomb's law. Force equals the charge of the nucleus, charge of the electron divided by the distance squared. So this first one, what row are we in, really looks at the size of the atom. How many protons looks at this guy right here. If this distance is relatively the same, then we'll go to this charge here. This one really here is the effective nuclear charge. How many electrons? You should be aware, as we learned in the last section, that electrons can repel. So we can get a slightly bit larger. Okay. This last one would be relatively small for this, but if you add electrons to an atom, only adding electrons, then electrons will swell slightly, making it slightly larger. Of course, we know, not a lot, but we know that if you increase the distance, then it'll be a little easier to remove because the electron's a little farther away from the shining light of the nucleus. All right, so who has the highest ionization energy? So let's walk through our process. First is energy levels. So you could find them on the periodic table. This is sodium, magnesium. All right, so I got a periodic table right here. We got sodium right here. We got magnesium right here, and they're both in the same energy level. So that's 1, 2, 3. So they're both going to be in the same energy level. So that's step 1. Okay, that didn't help me out any. Which means that the relative distance to the outer electron. Now, when it says who has the highest ionization energy, we're referring to the first ionization energy, which is this electron right here and this electron right here. Could also be this one here. Doesn't make a difference which one, because they're the same. So in this situation, by the first rule means that my distances are pretty close to the same. Number 2, okay. Now, with that being said, who's got more protons? Okay. Now, magnesium's got 12. This guy's only got 11. So that means this guy's got a greater amount of Coulomb attraction. So, in that case, who has highest ionization energy? Magnesium. And why magnesium? It's got more Coulombic attraction. Why? Because it's got increased number of protons. At the same distance, it's more harder to remove this electron, more difficult. I don't think more harder is a word, sorry. But it's more difficult to remove, it requires more energy to remove because it's got to break a stronger bond because it's got more protons. All right, so we have a overall trend of here is the increasing to the right, increasing up. Helium, you might think of as being as they have the highest ionization energy. Right? Lowest ionization energy would be francium. Okay. All right. So we get some practice here. Okay, again, we're going to walk through this on your own. You want to pause this and try it out and see how this works. Okay. Practice circle the largest ionization energy. Or you can draw a little greater than less than sign. I might do that instead. So calcium 2 plus. Here's an interesting one. Keep in mind that the calcium, when it's 2 plus, calcium typically has only 2 valence electrons. So it's going to lose both of those and it's going to expose a much smaller atom. So this one is larger because we're not pulling off the same atom. Okay, we're actually pulling off an atom that is, let's grab this periodic table quick. So calcium's here, we're actually going back to argon. So if I were to sketch this out here, it would be more of a calcium with a 1, 2, 3, 4 energy levels, and of course that's this guy, electron, electron. These two are easier to move than this one. That's what the question's asking. And that's why that one's bigger. It's closer. We lost an energy level. We're not in the same row of the periodic table anymore. Calcium and potassium. Okay, let's find it. We have calcium here and potassium here. Same energy level. More protons, more difficult to remove. That way, this one there. Calcium, argon. Okay, find them. Calcium, argon. Again, not the same energy level, so removing the outer electron, argon would be more difficult. Why? It's closer. All right, calcium 2 plus and argon. Now, keep in mind that this guy lost its electrons. It's isoelectric with argon. Is it argon? No, it's not argon, but it's isoelectric with argon. Okay, so they're in the same spot. They're in the same row. So first check is done. We cannot use the row of periodic table. Now it goes for more protons. Who's got more protons? Calcium has more protons. So the electrons look the same, but calcium got 2 more protons here than argon does. So it doesn't radiate quite the Coulomb attraction that argon, more Coulomb attraction than argon would. Fluorine versus fluoride. Okay, so the same row, obviously. Fluorine's here, but fluoride's isoelectric with neon. Okay, so that being said, they're in the same row, the same number of protons, and it just comes down to our slight little difference that because fluoride swells a little bit due to electron repulsion, electrons a little easier to move. Scandium versus why would I think that would be yttrium? Kind of a cool name. So let's find scandium. Scandium's here, yttrium's here. Okay, we don't know anything about these atoms. We do know that the yttrium is bigger, so electrons farther away. So therefore, this one is more difficult to remove because it's smaller. Okay, and I wrote this one backwards here. We know that this is easier to move because it's farther away. So there. Okay. Nitrogen nitride versus neon. Okay. So that seems strange, nitride, but really it seems strange what I do with that. Well, what's the isoelectric with? And then we'll compare that guy to this one. So nitrogen gained 3 electrons, neon. Okay, so it's isoelectric with neon. Well, it's just neon. Similar. Okay, so same number of energy levels, but the neon's got more protons. Okay, so this guy would be bigger because more protons, more Coulombic attraction. All right, next topic. Student hypothesis: oxide has a lower ionization energy than oxygen because it has a full shell. Just for nullify this hypothesis. Well, it is true that oxide does have a full shell. It gains 2 electrons like this, versus oxygen, which is just 1, 2, 3, 4, 5, 6. This is maybe one of the largest um, misnomers or things that kids typically get wrong as they move through chemistry. We want to answer these questions in terms of Coulombic attraction only. Okay, so again, don't go by this idea of a full shell means more stable, less energy. All I want to do is say, okay, what energy level is it in? Okay, how many protons and how many electrons? And you'll find that this guy here, electrons are a little bit farther away, so therefore it has a it's slightly easier to remove these electrons than these ones. Why? Because, well, it gets slightly larger. Okay, you should note that removing successive electrons always gets more difficult. So removing successive electrons, spelled that wrong. Wowzers, that's horrible. Successive electrons gets harder, gets more energy. Okay, so whether I go from, if I had like this, oxide, removing one electron takes X energy. Next electron will take bigger than X. This electron even more, and that is the one we're referring to on this guy. And anytime I remove the next electron again, it gets even harder. It always gets more difficult to remove successive electrons. And we don't want to deal with that in anything other than Coulomb's law. Now you notice that Coulomb's law is the force of attraction equals the charge of the nucleus times the charge of an electron divided by the distance squared. So I guess if you're removing successive electrons, and I guess if it always gets more force required, then this must be continually getting smaller as I pull off electrons, which is correct. Now these two here on the oxide are just due to repulsion, but this one, same thing. Okay, eventually it could get a lot harder if we change energy levels too. So. All right, that's a common misnomer. Can remove multiple electrons, first ionization, second ionization, third ionization, and like I just kind of talking about it a second ago, yeah, you can. All right, so for aluminum, okay, so aluminum, okay, goes to aluminum plus one electron. This is the equation. And we're going to add energy into this process. I'm going to call this E1. And aluminum plus 1 goes to aluminum plus 2. There's the electron that I tore off. I have aluminum plus 2 goes to aluminum plus 3 plus 1 electron. E2, E3. Okay? And I could even pull off another electron. I would call this E4. And I have aluminum plus 3 goes to aluminum plus 4 plus 1 electron. Now, what do you know about these energies? Okay, let's draw a Lewis dot structure of this, or I should say a Bohr structure. So aluminum's got, it's got 13 protons, electrons if it's neutral, 3 energy levels. Okay, so with that said, 1, 2, and 3. I'm pulling off this electron, this electron, this electron, and this electron. This is B let's say E1. This one could be E2. This one could be E3. And this one, kind of a little bit different, is E4. Okay? So all of these guys, it gets more energy. So E1 is less than all the rest of them. Okay? But E1. But E4 is considerably greater than E3. And, that's something that you'd want to kind of understand, think about. Why? Well, it's an entire energy level closer. Okay. All right. This is what there we go. We just did that. Circle, electrons removed. All right. And then, can I remove multiple electrons? Yep. So here's an example of this common, typical question. An atom has 3 electrons removed, and notice we got 1 electron, 738, 2 electrons, 1450. It gets more difficult. All of a sudden, boom, we got 7730. Wow, that's a lot bigger. What might you notice about this data? Again, you notice that this is considerably bigger. Okay, so this is likely an atom that has 2 valence electrons only. So what atom might this be? Well, some atom in this second row. Beryllium, magnesium, calcium, strontium, barium, Ra. I don't even know what that one is. So, yeah, something with 2 valence electrons. We can't tell exactly what it is. There we go. Our big increase. They're indicating this might be magnesium. Possibility. We don't know for sure. But notice the 2 valence electrons. Pull the first one off. Pull the second one off. And now we're trying to dip into a closer energy level. Therefore, the distance is much smaller. This is an interesting chart, just showing ionization energies. You'll notice that there's a little band where it goes from small to big, small to big, small to big, and as you get farther and farther out, it gets you see the trend continuing, and that is because you're dipping into an energy level. Okay, now for example, aluminum is between the 3rd and 4th because it has 3 valence electrons. Aluminum, every time we go a little farther, we get one more step down because we gained one more valence electron. So it takes a little longer to break into the next shell. All right, sample question. The first 5 ionization energies of a second period element are listed below. Okay, so second period would be referring to on the periodic table. That's referring to the second row of the periodic table, which is right here, which quickly identifies the element that best explains the data table. So we're looking for a big, significant jump, and in this situation, I kind of see a big jump right here, and it's really only asking us 2 of these guys, boron and nitrogen. So we're looking at boron, which is located here, and nitrogen going here. So at this point, I think it's probably going to be boron, because it's going to drop back to helium. All right, so we're looking to cross out these 2. And why? And the reason is because it has 3 valence electrons. And that's why that's right there. And I believe that comes to the end. Thank you very much.